In this lecture, I'll introduce you to triple integrals. So the idea behind triple integrals is rather than using a thin box with a small rectangle at the bottom and taking the volumes of these and summing over to get the volume of the solid, we're going to use boxes which are small in all three dimensions. So the picture more looks like this. So we have a delta z now, as well as the delta x and the delta y in terms of the dimensions. So the volume of this small piece of the box will just be the product of those. And so we're going to have delta v equal to delta x, delta y, delta z. And to get the total volume, we're going to sum over all possible boxes like this and have lots of little boxes like this that we're adding together. So the volume is going to be a sum of these smaller boxes, and we want to know what happens as the number of boxes goes to infinity and the dimensions on every side of the boxes goes to 0. And as you might expect, we're going to get a triple integral then, and the dv here is coming from the delta v, and the triple integral is coming from the sum. And we're integrating over the solid g that we're looking at. In this case, this would be the solid. And that dv is going to be, this is going to be delta x, delta y, delta z. So dv is going to be dx, dy, dz in some order. It doesn't have to be this order. It could be in any order. So it is possible to integrate a function. Before, what I was doing was just dv, and so that would be the volume that we were computing if we had a 1 here. But if we have a function there, you might ask what that mean? What's be the point of having a function there? Normally, this would mean maybe a volume in 4 dimensions. Well, you could look at it that way, but it can have other meanings that are significant. For example, if this F is representing the density of a particle in your solid G at a certain point x, y, z, then this would represent the total mass of the object. So this does have some meaning. Here would be a simple theorem telling you how to set up a triple integral when you have a box, and nothing surprising here. The x is going between a and b, the y is going between c and d, and the z is going between k and l, because those are the limits on x, y, and z that you're given for the box. The usual properties of triple integrals, same properties we had for single variable calculus or for double integrals. You can take constants outside the integrals. You can take the integral of a sum as being the sum of the integrals, and the same thing with the difference. And this is similar to something we looked at a little while ago with a double integral, but also in a single variable case, there's something similar. But you can take the solid here, in this case that we're doing the triple integral over, and break it up into 2 pieces and do the integral over each of those pieces separately and then add those together. So for the extra z here, basically you're going from the bottom surface to the top surface of your solid. Imagine going straight up in the positive z direction, and you're going to hit the bottom surface first and then the top surface. So the bottom surface goes here and the top surface goes on top. This is telling you basically how this book imagined setting it up, and I kind of imagine something different. So I think this is a good thing to keep in mind. What you want to do is to look at what's happening to the outside 2 variables first. So in this case, since dz is here, this would be dx, dy, or dy, dx. So you want to figure out the limits on that first, and what we'll do is figure out what region in the xy plane we have and set up those integrals first for this double integral here. So just treat this like we did with the double integral a little while ago. We're going to set up the limits of integration for a certain region in the xy plane that is basically the shadow of the solid in the xy plane. And we'll talk about that in a little bit. And then for z, we do what we said, taking the bottom surface to the top surface. So I would do step 2 before step 1 here. First, figure out what's going on with the outside two variables, in this case dx, dy, by setting up the double integral, and then figure out what's going on with z second. I wanted to emphasize here what this means. So you're integrating with respect to z first. That's why I put this here. And then after you solve that integral, you're integrating with respect to y. And then after you solve that integral, you're integrating with respect to x. Now, the limits of integration, you can have x and y on the inside here because the inside variable is z, you put parentheses around this, then anything that's on the outside, those variables, x and y, the limits of integration can depend on those x and y. So if you imagine doing this integral first, and you have x and y out here, then these limits of integration can depend on x and y. If this was a dx and dy dz were out here, then the limits for dx can depend on y and z. So you would have functions of y and z here. So whatever's on the outside of the first parentheses, the inner parentheses, those variables can be in the limits of integration here. Okay, now notice what the effect of that will be is that when we integrate this with respect to z, you're going to be replacing z with these two, so you end up with a function of x and y. So after the first integration, you have a function of x and y, so you can integrate that with respect to x and y. Now we're integrating with respect to y next, so we put parentheses around that. And the limits of integration now can depend on any variables that are outside this second set of parentheses. So they can depend on x. So now we can use x in our limits of integration here. And that has the effect that since this depended on just x and y, when we integrate with respect to y and replace y with these, we have a function of just x here. And so it makes sense then to integrate with respect to x to get a number. So these are going to be numbers here. Now there could be some constants, but we want to view them as being numbers. So we have numbers there. We have functions of a variable here where the variable is on the outside, the x here. And here we have functions of variables where these functions can depend on the other two variables that you're not integrating with respect to. So that'll be the general setup. And when I say these are functions of x or x and y, they can be numbers. Your function of x and y might just depend on x too. But there's some functions that can depend on x and y, but they don't have to. And the same thing here. So let's do some examples. Now this looks like an example. If you saw this on a multiple choice test or on any kind of test, you might suddenly decide that you want to go to the next question. It's not as bad as it looks, and probably of the examples I'm going to do, in some sense, it's the easiest. You have a big mess here, but you're integrating with respect to z. So z is the only thing here that we're integrating right now. This is just a constant. So we're going to get this constant, which I'll just call a mess right now. And I'm integrating with respect to z. I'm going to get z squared over 2. Now, I'm going to also just call this a here. So I'm going to set this up. This is the inside integral with respect to z. So I have a mess times, this is the mess, times z times dz. And I'm integrating from something, I'm just going to call it a, minus a to a. Okay, so this a is just the square root of x squared plus y squared plus 3. So I'm going from minus a to a here. And notice I get mess, that's just a constant, doesn't depend on z, z squared over 2. Evaluate from z equals minus a to a. What happens, I plug in a, I'm going to get a squared. I plug in minus a, I get a squared. So if I rewrite this as 1/2 mess z squared, I get the 1/2 mess z squared now, where z is replaced with a and minus a. And I get a squared both times when I square, so I'm just getting a squared minus a squared and ending up with 0. So when I do the integral with respect to z, I'm just going to get 0. So you're integrating 0 then with respect to y, you get 0, and then 0 with respect to x, you're going to get 0. And the final answer is 0 then. So this messy integral was really just 0 because that mess doesn't really come up. When you integrate with respect to z, you're going to end up getting 0. So let's look at this example. We want to write a triple integral that represents the volume. So we're going to be doing a triple integral of 1 dx, dy, dz, or some order. Z equals this is on top, and this is on the bottom. Now you can see which one's on top, not just by reading, but also because if you look at the origin here, you're going to have z is 0 at the origin on this one. And when x and y are 0 here, z is minus 9. So this is going through the origin, the top one. And this bottom one is going through minus 9 on the z-axis. So this one's below this one, at least on the z-axis. And the surface looks like this. This is a hyperbolic paraboloid, which we have discussed earlier. That's on top. And the bottom is a paraboloid, elliptic paraboloid, and that's on the bottom here, that elliptic paraboloid. So how do we want to approach this? We want to figure out the volume of this unusually shaped thing here. And how do we get that? So the idea is to go ahead and figure out first what this intersection is between these two. So if I take a point x, y, z in here, I want to know what's going on with x and y. So they intersect when these two are equal, when x squared minus y squared equals 2x squared plus 8y squared minus 9. So in other words, if I take a point where they intersect, so this equation is true and this equation is true, then since z equals both this and this, these two have to be equal. So that's going to be what's happening with x and y on the border. Now, why do I care about x and y on the border? The idea is to figure out the region in the xy plane. So ideally, you basically have a sun light way up here or further up than this, and you're trying to look at the shadow in the xy plane. And that shadow in the xy plane will be the region you're integrating over. Now, unfortunately, this is not all above the xy plane, so when I say that, you have to imagine it is. And so what that shadow would be if this were above the xy plane is what we're interested in. So imagine the sun up here, you have this solid xy plane down here. What is the shadow? And that shadow is going to be determined by the intersection because that's going to be the border of the shadow. Down here, we're going to have that being the border of the shadow, whatever that shape is. And then the x and y are going to be whatever is inside that. That's also going to be part of the shadow. So to figure out what's going on in the xy plane, we have this equation. And I'm going to go ahead and move the x squared over, move the y squared over here, bring the 9 over, and rearrange, and put the x squared plus 9y squared is 9. Okay, that's just rearranging this. So you might recognize what this is. If you divide by 9, it might be easier. You have x squared over 9 plus y squared equals 1. Now, you don't necessarily need to know it is, but it does help. And where did this picture come from? Well, the way I think of it is that I want to know where this crosses the y-axis and the x-axis. This crosses the x-axis, where y equals 0, by setting y equal to 0. So this intersects the y equals 0, the x-axis, when x is plus or minus 3. So that's where those came from. This is minus 3, this is plus 3. It intersects the y-axis. The equation of the y-axis is x equals 0. So I plug in 0 here. You can see y is plus or minus 1. So we have minus 1 and plus 1 where it intersects the y-axis. So this is roughly what our ellipse looks like. And this is going to be the shadow. The shadow is what's inside here. So I have this ellipse. It doesn't look like an ellipse, but again, we're talking about the shadow of it in the xy plane. And it's going to be this shadow inside this ellipse and on the boundary. And the boundary, again, is really coming from the intersection of those two surfaces that we just calculated. So I'm setting up the integral now. And again, as I suggested, we're going to do dx dy first. And that we just do by looking at this region in the xy plane. The x and y that are inside here, so the x, y, z, you just look at the x and y part, and that's going to be inside this ellipse. So the x and y's are just what's inside here. So those are the points x, y. So I'm looking at that region, this region here, this ellipse, and trying to figure out the limits of integration for x and y. Y is going from minus 1 to 1. It's on the outside, so I want numbers here. It's going from minus 1 to 1. And just like before, when we would do this, we want to take a horizontal line and see the first curve we hit here going to the next curve we hit. Now it looks like the same curve. You have this curve on this side and this curve on this side, but they're really the same curve. But how do we figure out what this equation of this curve is? Well, this was the ellipse. I'm interested in knowing what x equals here. You want to go from x equals something to x equals something else. Well, we solve for x. We bring over the 9y squared and take the square root. So we're going to get two things when we take the square root. We're going to get either a plus or minus the square root of 9 minus 9y squared when we take the square root, right? I bring the 9y squared over, take the square root. I'm either getting this or this. Well, you can see this one, we have x being negative, so that's this part here where it's negative. And on the right, we have where x is positive, so that's this part. So we're going from the negative part one here, this one, to this one. So that's why the limits of integration look like this. I've taken out a 9. The square root of 9 is 3. So I've taken that outside the square root. But that's just coming from here for the lower limit on x, and from this for the upper limit on x. Okay, so we just get this, then, and this, and we get what we want. The limits on dx. Now, what we want to imagine is taking a point inside here, some xy inside here, and then you're going to go straight up and down along in a z direction. Now you want to go from the lower curve to the upper curve because you're going in the positive z direction, really to figure out the limits of integration. So you're going from the bottom curve first, and then to the top curve. So the limits of integration on z, you're hitting the bottom curve first, which was z equals the 2x squared plus 8y squared minus 9, to the top curve, the hyperbolic paraboloid, z equals x squared minus y squared. So you're going from the bottom curve to the top curve. So that's the setup then for this triple integral, and that's what the problem was asking for it, just writing the triple integral down. And this would represent the volume then of this solid. Let me do another example. Here we have a triple integral, and all I'm asking you to do is to rearrange, switch the order of integration. You had to do that with double integrals, sometimes to even evaluate it. So I'm imagining now I want to rearrange or switch the order of integration. So it's going to help to know what the solid looks like, so that whatever we're integrating up here is determined by the limits of integration as far as that solid goes. So you need to figure out what that is. Let's look at what we have information-wise here. Y is going from 0 to 1. X is going from Y to 1. So what would that look like in the XY plane? So I have an X and Y axis, say here, just to pretend here for a second. And I have Y is going from 0 to 1. For each fixed Y, you want X to go from X equals Y to X equals 1. So what does that look like? Well, you want to imagine then that you have Y equals X or X equals Y, and X equals 1 as boundaries, and then you have the X-axis. So you basically have a triangle where one side's along the X-axis, then you have X equals 1, and then you have Y equals X. And this will be an isosceles right triangle. So that's what's happening in the XY plane. And we want to go from that triangle, we want to go from z equals 0, so that's the XY plane, up to whatever this is. What is this? Z equals the square root of 1 minus x squared. See, that z squared equals 1 minus x squared. That's x squared plus z squared equals 1. What does the graph of x squared plus z squared equals 1 look like? Well, in the xz plane, x squared plus z squared equals 1 is a circle centered at the origin of radius 1. But now there's a y variable in this. We're in space. So we have that circle, and y can be anything. So we imagine moving that circle in the y direction, either backwards or forwards. And we're going to get a cylinder where the center of the cylinder is the y-axis, and the radius of the cylinder is 1. So the picture ends up looking like this. And let me elaborate a little bit here. So this is the triangle on the bottom. This is the origin back here. Going along the line, this is 1 here on the x-axis. And then this is x equal to 1, and then this is y equals x. So in the xy plane, we have that triangle y equals x, x equals 1, and the x-axis back here. For each fixed xy in that triangle, we're going from the bottom, which is the xy plane, and then we're going to the top, which is the cylinder. Now the cylinder, again, is where z equals the square root of 1 minus x squared. So we're going from z equals 0, the xy plane, to z equals the cylinder. So that's what the picture is showing us. Now we want to set up this triple integral with the order being dx, dy, dz. And what I want to do is now figure out what's going on in the yz plane. So how do we figure out what's going on in the yz plane? Well, when we were trying to figure out what's going on in the xy plane, we took a sunlight way up here and looked at the shadow in the xy plane, which would just be that triangle we're looking at. But now we want to look at the shadow in the yz plane. So we want to take the sun way over on the positive x-axis, so down at the positive x-axis, and look at the shadow in the yz plane. And just to keep in mind here, this is the point 1, 1, where y equals x and x equals 1 intersect. This 1, 1, 0 in space should be going down to just 1, 0 in the yz plane, where y is 1 and z is 0. So let me first deal with what the shadow roughly looks like. So this is the kind of shadow. I'm trying to imagine it looks something like this. I'm not saying it's necessarily even accurate, but I'm just saying that that's what I'm trying to do. I'm trying to figure out what this region is in the yz plane, what that shadow is when I take the sunlight way over here on the positive x-axis and look at what happens to this solid. So where is this coming from, this curve? Well, that's going to be coming from this curve, where these two intersect, this plane and this cylinder. So where did they intersect? So let me make that solid there. So that's a red or maroon line, if you want, going here. I want to know what's the equation of that maroon line, at least what's going on with y and z. So I want to know what the shadow is. So what's going on with y and z on this line, this curved line? So that's the intersection of these two. This is just the cylinder we talked about, the z equals the square root of 1 minus x squared. And what about this? Well, this is coming from this line down here, which was y equals x, and we're going straight up. Z can be anything, but that just means that this plane, the equation is y equals x. So this is the plane y equals x. We're taking y equals x in the xy plane, just going straight up. Z can be anything. So this is y equals x, and this is the z equals the square root of 1 minus x squared. So I want to know where those two intersect. And again, what I'm really interested in is finding out the equation of this in the zy plane. So I want something that depends on z and y. So I know z equals this, I know y equals x. And so if you have a x, y, and z that satisfies these two equations, then what I can say is that z has to equal the square root of 1 minus y squared, because y has to equal x. So we get z equals the square root of 1 minus y squared, and that's what these points are satisfying as far as x, y, and z go. So this is what I'm graphing here, it should be, is this. Now this is actually a circle of radius 1 centered at the origin and in the zy plane, or the yz plane. So that's the region I want to integrate over first. We want to see what's happening to z. First, it should be between two numbers, because we're on the outside here. And z is going from the origin to 1. Remember, this was a cylinder of radius 1 centered at the origin, the x squared plus z squared equals 1. So there should be 1 up here. So it's going from 0 to 1. So let me go ahead and set that. Again, we do want these to be numbers, so this should be 0 and 1. 0 to 1. Now what about y? Well, y is going, well, again, just imagine drawing a straight line here. I can do that again. A horizontal line in the yz plane, and I want to go from the leftmost curve, which is here, where y equals 0, to this curve, where y equals, that's a good point. We don't have y equals, we have this. So we have to solve for y here. So y equals 0 to y equals whatever it is on this curve. So we need to solve for 1. Z squared equals 1 minus y squared. So y squared is going to equal 1 minus z squared. And then y will equal plus or minus the square root of 1 minus z squared, but we're interested in the plus part because y is positive here. So y will equal the square root of 1 minus z squared. We're going from 0 to, again, y equals the square root of 1 minus z squared. Finally, we have to deal with x. So we want to take a line going in the direction of the positive x-axis. So we want to go in the positive x-axis. And we want to go from the back of our solid to the front of the solid, because we want to go in the positive x direction. So the back of the solid, x equals y. That was y equals x or x equals y. That was this plane. To the front of the solid, that was this cylinder, so I need to solve for x here. Z is equal to square root of 1 minus x squared on the cylinder. So z equals this. Squaring both sides, z squared equals 1 minus x squared. So x squared will equal 1 minus z squared. Take the square root. Again, x is positive. So it's going to be the square root of 1 minus z squared. So here, x equals the square root of 1 minus z squared is the same thing as z equals the square root of 1 minus x squared. So x is going from this plane, x equals y, to this, where x equals the square root of 1 minus z squared. X equals y, square root of 1 minus z squared. So we get that then for our limits of integration on x. X equals y to x equals the square root of 1 minus z squared. So we are actually done with this problem now. We've set up the limits of integration for this triple integral. We have z going from 0 to 1, y going from 0 to the square root of 1 minus z squared, and x going from y to the square root of 1 minus z squared. So that's what's involved with switching the order of integration. Let's look at this example. So we want to find the volume of a solid enclosed by the paraboloid x equals y squared plus z squared and the plane x equals 16. It goes through the origin, as you can see. And when y and z are not both 0, this will be positive, so x is going to be positive otherwise. So it's starting at the origin and opening up in the positive x direction, paraboloid. So we're going to get then this paraboloid picture looks like this. We have a paraboloid goes through the origin for the vertex, opening up in the positive x direction. And then it's cut off someplace where x equals 16. So this is just a plane x equals 16. Now, in terms of shadows here, it's easy to project the shadow of this onto the YZ plane. So if I have the sun way down the positive x-axis and I'm looking at the shadow, it's just going to be this circle here. So we're just going to get that circle for the shadow in the YZ plane. I just want to put that circle in the YZ plane. But it's a circle of radius 4 because x equals 16. So 16 equals y squared plus z squared. So it's just a circle y squared plus z squared equals 16. So it's a circle of radius 4 centered at the origin in the YZ plane. That's the shadow. So setting this up, I'm going to go ahead and put y and z on the outside because I know easily what that shadow is and I can just integrate around that circle. So this is the setup I have. I put dz dy, and dy dz would be fine, but I put dz dy and I'm going to go ahead and look at what's happening with y first. So in the shadow, y is going from minus 4 to 4 again because that was this circle. 16 equals y squared plus z squared. And then z will go from minus the square root of 16 minus y squared to plus the square root of 16 minus y squared, the bottom of the circle to the top of the circle. So again, this setup here is related to an old problem 11 we looked at with setting up the limits of integration for circles in double integrals. So we have those limits of integration, dz dy. Dx now we figure out by going in the positive x-axis direction. So we're going in this direction. We hit this paraboloid first. So that's where x equals y squared plus z squared. And then we hit this plane where x equals 16. So x equals 16 is there. So those are the limits of integration on x. Now this integral I'm going to do a strange way because I just want to show you some of the possibilities here. And what I'm going to do, and this sounds a little silly, but you'll see why it works nicely, is I'm going to go ahead and replace x with z and z with x. I mean, what's in a name? So if I call x z and z x, it doesn't change the value, it's just changing what the letters are. So I could make z t here and x r, and then go ahead and replace all the z's with t and all the x's with r's, and this is still going to have the same value. It's just giving variable x and z a different name. So what I'm going to do is call x, z, and zx. So I replaced x with z. So that's not an x here. That's just replace this x with z then. I'm going to replace all the z's with x. So I have a z here that's been replaced with an x, and I have this z here that's replaced with an x. So I replaced the z's and x's with each other. But again, it's just calling them a different name, but it should have the same value, just have different names for the variables. Now, why is this easier? Well, first, if you integrate with respect to z, you're just going to get z evaluated from here to here. So that's just going to give me 16 minus dx squared plus y squared. So I'm taking z, when I integrate this, I get z, and evaluating it from y squared plus x squared to 16. And this is what I get. 16 minus y squared plus x squared, or x squared plus y squared. Now maybe you can see why I wanted to change the variable names. I'm integrating dx dy here. We're in this circle of radius 4 centered at the origin now in the xy plane, because x and y have these limits of integration. And why is that advantageous to us? Well, we can change the polar coordinates. We're just integrating around a circle. So x squared plus y squared is r squared in polar coordinates. We're integrating around a circle, so theta is going to go from 0 to 2 pi all the way around the circle. And the radius is 4, so r is going to go from 0 to 4. And then dx dy gets replaced with r d theta. Now, why would that be helpful? Well, imagine integrating this with respect to x. You're going to have an x cubed over 3. You're going to evaluate it at these. You're going to end up with 16 minus y squared to the 3 halves. Things start to get messy. But if we switch to polar coordinates, what we have, again, theta going from 0 to 2 pi inside this all the way around the circle. And the r is going from 0 to 4 because it was a circle of radius 4. 16 minus r squared, and dx dy becomes an r d theta. But you can see that's an easy integral to solve. You just integrating 16r and r cubed, you're getting some number there, and then you're just integrating a number d theta, so you get 2 pi times that number. Now I'm not going to go through the arithmetic there, it's just straightforward, but you get 128 pi then after you evaluate that. But that's much easier than trying to integrate this with respect to x or y, and those would give you trouble if you try to do it. So switching to polar coordinates helps, and we're able to say then that this is 128 pi. But notice it helps in terms of switching to polar coordinates because we at least typically think of polar coordinates as involving variables x and y that we're replacing with r cosine theta and r sine theta, x squared plus y squared is r squared. And we can do that easily here once we get the integral looking like this. But that helped then to switch the z and x around to get to look like this. So that's the last example I was going to do, and that should get you prepared then for doing the homework.